Hello. So thanks very much also to the organizers. So I'm Marc Huertas-Cumpany. I'm a professor at the Paris Observatory in the University of Paris-Diderot. And now I'm spending some time here at La Laguna for this year. So my role here is to talk about deep learning in astronomy. So there will be some overlap with what we've heard before, because to introduce deep learning, I need to introduce machine learning first. But it will mostly focus on the techniques that we call now deep learning, or as opposed to more classical machine learning. So I will start also by asking the question of who's already worked with deep learning for their research, not machine learning, but deep learning. Okay, not so many. So before I start, I must say that there's a huge amount of literature around the web, because this is a boom now. And so I'm not reinventing the wheel. Several things that I'm using here, or some of the slides I will use in my course, are taken from the web and from resources online. So I'm listing here some of these resources. Thanks to all of them. And you are, of course, encouraged to look and go and have a look at all of those. Some other preliminary notes. So as Dalia said, and as opposed to what Michael showed, I'm not a machine learning researcher. So I'm just a user of machine learning, and in particular deep learning. I've been using machine learning for the last 14 or 15 years, more or less, but from a user perspective. So I won't be entering into the mathematical insights of how these algorithms work. I will a little bit just to have an idea of how these work, but I'm not doing a formal presentation of mathematics, just as Dalia did. My goal here is that you have a global understanding of how these AI techniques work, and hopefully that you can use them for your research. So to trigger some interest and that you are able after this course to see, oh, this could be interesting for what I want to do, and to have an idea of how this works. So what are we going to learn? And when people talk about machine learning, there are several words that come in: data mining, machine learning, big data, artificial intelligence. All these words sum up together, and sometimes there's a bit of confusion in this. So let's have an idea first what deep learning means and what is the artificial intelligence. I'm quoting this from Alan Turing, which says that what we want is that a machine can learn from experience. And basically, this idea of artificial intelligence, or having robots or machines that are intelligent as humans, is old, let's say from the 50s, as we already saw this morning. But basically, this is a global objective, and we are still far from it. So in the 90s or 80s and early 2000s, this, within the artificial intelligence, it was kind of reduced to some what is called machine learning. And this is how machine learning started to flourish. And these are the algorithms that we have been seeing. So basically, you are trying to find boundaries or classify objects with some kind of criteria. And it's only recently, let's say after 2012, I would say that there's this boom in artificial intelligence, which is driven by deep learning. And some of the major breakthroughs that we have been hearing around come from this deep learning, which I would say is a sub-branch of the machine learning, which is a broader field. Now, AI is getting an amazing media attention, and there are a group, I'm biased towards the French system, of course, but this is lots of big companies are investing a lot of money in artificial intelligence now, and there's lots of academia also going on. Well, this school is a proof of this. So there's a growing interest on these techniques. This is a paper I just plotted now, which is the number of citations from the ADS database using machine learning in the abstract. And you see how this is exponentially growing, or even more, faster than that. And I want to join my colleagues saying that we have to be cautious on this. People are using this as black boxes. It's fancy. It's easy to use now because you have scikit-learn. You have Python packages, which are very easy to use. And people start using this for the research blindly. And we see the number of papers. And it doesn't mean that it's used properly. So I think it's important to attend these schools and have younger generations learn on how these techniques work. This is also the same kind of plot about conferences and workshops organized worldwide with the term deep learning or machine learning, and you see how this exponentially grows too. So why is this AI fever around? And I will say that I will simplify this with a very simple picture, and it's before 2012, trivial human tasks like distinguishing cats and dogs remain a challenge for computers. So the typical accuracy in determining if in a picture of an image of an animal is a cat or a dog was around 60%, so barely above the random decision. And after 2012, this has become trivial. So now accuracies are above 99%, I would say. We have deep networks, machines that classify thousands of classes of images with very high accuracy. And so suddenly, so the machine learning field was kind of, I would say, stagnated at some point, because for many years we have been playing with the same algorithms, facing challenges that we couldn't solve, and suddenly deep learning opens a new field, not field, but a new range of possibilities that you can do that you couldn't do before. This is maybe a change of paradigm, but I don't know. So I will enter into details into this, but here is how the typical accuracy in determining or classifying objects. So basically, this is what is driving the AI revolution. And you see how after 2012, the accuracy or the error rate decreases with the advent of convolutional neural networks, which are the building blocks of deep learning. And you see that since 2015, we are below the human error. So neural networks are doing better or less errors than humans in classifying objects. So why is this breakthrough? And why, so to come back to this idea of, to this mix of terms, because very often artificial intelligence comes with big data, and it's not necessarily the same thing. However, most of this breakthrough in artificial intelligence is actually driven by big data, because we have more available large data sets to train. And this is something I will emphasize later on. But basically, with some technology, because now, so we have the ways in terms of hardware to train these complex models, and this is thanks to GPUs, graphical processing units, that can process and train these algorithms efficiently that we couldn't do before. But basically, there is no major revolution idea. So nothing changed. So in fact, the idea of deep learning or convolutional neural networks is very old. It's from the 80s. And so there's no major change or a major theoretical idea. It's just a matter of having the right technology and the right amount of data now, thanks in particular to social networks, for example, in which we all voluntarily put some data in it. So what are we going to learn in this course from my point of view? So I will try to show you some basics of what we call classical machine learning, although I don't like this very much. But this is mostly covered by my colleagues, but I will introduce a little bit. So I think it's not bad to have some overlap and different point of views on the same ideas. And I will jump to the basics of deep learning, and both supervised and unsupervised, so I need to cover both. So probably I won't go into much details as my colleagues, but I will try to give you some examples of how we can use deep learning for both supervised and unsupervised problems. Again, it's not a theory course, it's more very practical. I hope this will be useful for research. I'm an extragalactic astronomer, also call me astronomer, not machine learning expert. So I apologize in advance for all the biases I can have in extragalactic examples when I will quote examples of use. So why do we need these tools in astronomy? Why do we need deep learning? And So I guess it's obvious, since you are all here, that with the big data revolution has arrived to astronomy, and we have heard already about this project, so I will go very fast. But basically, we have next generation of surveys driven by Euclid, WFIRST, LSST, and you see the number of objects as a function of the year, how it's drastically increasing, and in the next couple of years, we have orders of magnitude more objects to deal with. I like this plot, I always show it, but this gives you a graphical idea of how things are evolving. And basically what it's showing here is a function of the year, the area observed by the Hubble Space Telescope. So in imaging with the different cameras, so as a function, this is the launch date more or less, and so this is the sum of all the cameras, so the total area observed by HST. And you see that this is most of the knowledge of deep fields that we have, or extragalactic high-resolution imaging, comes from HST. So basically, all of the knowledge we have acquired over the years comes from an area of the sky which is around 10 square degrees, which is tiny. And so I'm now going to launch this video, and you will see what happened when Euclid is launched and what Euclid will do. So we have heard about SST. I come from the European side, so I will show you about Euclid. And this is what Euclid will do. So this is the area that Euclid will observe. Now it should be switched a little bit to 2022. But you see how it drastically changes the amount of data it will receive of high-resolution imaging. And we will go out to 15,000 square degrees observed at high resolution or similar resolution to HST. And this is how all the HST fields go down. So you need to update. This is pretty obvious that you need to change the way you look at the data. And as we heard this morning, it's not only about volume, but it's also about complexity. And the data we are acquiring is more and more complex, particularly IFU surveys. So now we are acquiring 2D spectra. So for every pixel in the image, almost we are acquiring a spectrum. So the amount of information that is there and the way you need to process this information, it's completely different, and it's completely impossible to visualize this information by the human eye. So you need process or techniques to deal with this. So I think this is very important. It's not only about volume. Big data is not only about volume, it's also about complexity. And we heard this about this morning too. And this is observation, but we also have simulations. And I'm showing here some examples of cosmological simulations that we already saw this morning, but we are simulating more and more volumes. And a lot of information is encoded there. And linking the observation to the simulation is also a very demanding task that needs this kind of techniques. So what's the program for the week, again? So I will try to cover these different parts. Not all the parts will overlap with the hours, so I hope it's more or less overlapping with the 4 lectures I have, but it's not sure. So today I will go very quickly on an introduction of what I call classical machine learning. Again, I'll emphasize this difference between unsupervised and supervised, but I will go quick because we've already heard a lot about this. I'll go through what are the general steps to teach a machine in general, and I will show some of the idea of classical classifiers or classical regressors. Then, in the second part, I will focus on what's the building block of deep learning, which are neural networks. So I will again show a little bit of how the perceptron works, but in a more practical way, let's say. We'll talk about what's a layer of neurons, hidden layers, what's the meaning of activation functions, optimization, and the backpropagation algorithm, which allows neural networks to work, basically. And from these shallow neural networks, we'll jump to deep neural networks, which are called convolutional neural networks. I'll explain how these convolutional neural networks works, so convolutions work as neurons, some specific blocks of CNNs, which are pooling, dropout techniques, and some specific problems also linked to training these deep networks, like the vanishing gradient problem, and how do you overcome this. So this will be for supervised learning, and then I'll try to show some examples of unsupervised learning with deep learning. So image-to-image networks, so networks that are able to produce images or data, not only classifying. And this will introduce the unsupervised deep learning, so how you can use autoencoders. Also, Delia will talk about this also, but I will also add some notes on here. And I will jump to generative adversarial networks and how they can be used to anomaly detection in astronomy. And the last part will be about some practical considerations that I will hope will be useful for you guys when you are trying to train your networks, and how do you start training these and how to overcome the typical problems you will encounter. For the hands-on session, I will try to implement some of these things we learn. I try to probably set up a deep network to measure galaxy ellipticities, although maybe I will change a little bit the topic. This is a GitHub repository I have for a course I gave at the Euclid School. You can check it out here, but I will update it very soon. So again, the main idea here is that let's try to discuss as much as possible. It's a small committee. You are grad students or above. So please interrupt, ask questions. Let's make this a bit dynamic, not only just one direction lecture. So please ask questions and whatever you want. As for the software requirements, Python 3, I will use TensorFlow for deep learning, which is the framework developed by Google. And as a high-level library, I'll use Keras, which is, again, coded in Python. So for all these things, I need GPUs. So how many of you have GPUs or an NVIDIA GPU in your laptop? Only? OK. So probably we won't go through GPUs. We will try to do some kind of reduced data set to train your algorithms. Anyway, I sent some information to the organizers on the, at least so we will work on Anaconda and all the packages that you need to install. All algorithms work even if you don't have a GPU, but they are extremely slow. So this will be interesting also for you to notice how different it is when you work with, without GPUs and with CPU. So I'll try to reduce the amount of data so that we can work with CPUs even and get some results. That's good to know. OK. Any questions on practical things before I start with part 1? OK, so this will be just a quick introduction to classical machine learning. And there will be some overlap on what we have already heard. But I think it's not bad. So I will say that there is no magic in machine learning. And it actually, when you look at it, it's pretty simple. So we'll start with and I think all of us have done at some point machine learning, and we astronomers do machine learning all the time, which is finding classes or patterns in data. I'm showing here for extragalactic astronomers, this is obvious, a UVJ diagram. But basically it's a color plot that we do in many different fields of astronomy. And basically what you call here, every point here is a galaxy, and it's color-coded by the specific star formation rate, so the amount of stars that you form. And you basically see that these guys over here are objects with low specific star formation rate that we call quiescent galaxies, passive galaxies that don't form stars, and star-forming galaxies lie over here. And typically what we like to do astronomers is that to identify passive galaxies among the others, or put objects in classes. And when we do this, basically, we are trying to find, given this parameter space, a line in this plane that identifies, at best, the population of interest, in that case, which are passive galaxies distinguished from star-forming galaxies. And this is basically a machine learning exercise. This is what we do when we do machine learning. So basically, machine learning, as we saw already, can be put in this form in which you have a function of some parameters, and it gets you some label in that particular case. In our case, in that particular example, the label will be quiescent star-forming, passive or star-forming galaxies. This will be my target, my labels. And I will use some filters, so some measurements. I took the data and will use some filters to try to get this label over here. In the particular case are 2 colors, or 3 magnitudes and 2 colors. My filters are the U minus V and the V minus J. And this is the X, the filter space. And I will have a function that actually will map these filters into my label. And in that particular case, this function is done manually, just by inspecting this training set. And the training set is something for which I actually measured with spectrum or with another higher level or better measurement. I was able to, for a subset of galaxies, measure the specific star formation rate. So I know how many stars they are forming. I know the colors, so I can try to find what is the best boundary that identifies the population of interest. In a particular case, it's just the sign of this line over here. And this is done manually. And this is what is my network function. So basically, and now that I've trained this algorithm over here, I can get the same data, but without knowing, or data for other galaxies for which I don't know the specific star formation rate, but I only know the colors, and I will be able to use my network function, or my function, which is this line over here, to map the filter space into my label. So basically, give me the colors, and I can tell you if it's star forming or quiescent. Yes? So it's a specific star formation rate, basically, okay? So this is for a training set. So for a set of galaxies for which I may be using spectra, I was able to measure, or H alpha, measuring properly the specific star formation rate. So this is typically what is a training set. So I know the truth, let's say, which is the specific star formation rate, and I know a filter space, which are colors, and I try to find the function that maps my filter space into my label using a training set. This is typically supervised. Exactly. In that particular case, yes. So machine learning is about losing control of things. And classical machine learning loses a level of control, and deep learning goes a bit deeper, and you lose more control of what you're doing. So basically what you will do, if you approach this problem with classical machine learning, you will replace this by a general nonlinear function. Instead of using, I will restrict my problem to use a linear boundary or whatever. I will put here a general function, not necessarily this function, but I will replace this function by whatever function, which is parameterized by some parameters. Okay? In that particular case, some parameters W. And I will try to find the best weights that get me the answer to that particular problem in an optimal sense, given a metric. So, and this breaks the machine learning into two families, let's say, as we have already seen. The supervised, in which basically the machine is told what we are looking for. Again, so in that particular example I just showed you, we know that we are looking for passive and star-forming galaxies, and we can divide this into classification, as we've already heard this morning, or regression if you are measuring a floating number. And you have the unsupervised techniques in which the machine is not told what to look for. And as we've heard this morning, this includes clustering and also generative networks, which is exclusively deep learning. So deep learning, so again, this is what you will see this in this lecture, and this deep learning covers both of them, basically. So you have deep learning can do supervised or unsupervised. I will show you later on how deep learning works. So let's have a look at some examples of deep learning applied. And again, I think my colleagues are also right in the sense that deep learning is fun, is fancy, is complex, but it doesn't mean that you need to apply it for everything. So there are problems that can be solved without deep learning, with classical machine learning or with simpler algorithms. There are things for which you want to use deep learning. And I will try to show you some examples of what I think deep learning is useful for, and it's applied to astronomy. So one problem is essentially our cats and dogs. And our cats and dogs for extragalactic astronomy is what we call galaxy morphology. And for galaxy morphology, deep learning is extremely powerful. And this is a 100-year-old problem in which we are trying to classify or put galaxies in boxes, elliptical, spirals, irregulars. And actually, this is from a paper I wrote a few years ago. But basically, what you see here is that the agreement that deep learning reaches with visual classification is extremely high, around 95% or something, classifying galaxies into different classes. And basically, why is this so successful is not surprising. It's exactly the same problem, or not exactly, but because it's less well-defined, but it's similar to the problem of classifying cats and dogs. And in fact, this is a typical case in which more classical algorithms based on engineered features like SVMs, for example, work much, don't work so well. For example, this is from an earlier paper in which we were using SVM to classify between only two types of galaxies, early type and late types, and you see that the performance it's quite lower, only without 20% error or so. So this is a typical case in which you don't know exactly what are the best features, and deep learning is very powerful to this. Another example, for example, is for classifying lenses or strong lensing galaxies. This is again a problem of classification, and basically you want to find arcs around galaxies, and this is a problem that, again, with engineered features is complicated. You need to extract the properties of the lens and plug it into a classical algorithm. And actually, we did a challenge for the Euclid context in which we tried different algorithms and compared them. And you see that the 5 or the 10 first algorithms are all based on CNNs. So this is, again, a case in which SVMs or other classical algorithms come below. Also an example on regression, the first ones were on classification, but it's a problem of regression in what you try to get the parameters of the strong lens in the problem. So not only classifying if a galaxy is a lens or not, but getting the parameters. And again, deep learning is extremely powerful on this. What you can do, you cannot do it with classical machine learning. Also, very specific things to machine learning. They are extremely powerful, and I will talk about this during the last days, probably, on generating data. And for example, these are Sloan images, real Sloan images of galaxies as DSS, and these are galaxies which are fake, but are generated by the network. So the network is shown some examples of Sloan galaxies, and then it learns to generate new data. And this is what we call unsupervised deep learning, and you can generate and increase the amount of data. This is another example at high redshift in which, again, you generate fake galaxies, which are very realistic. And doing this with other kind of algorithms is extremely complex because you need to get all the complexity of the features if you have spiral arms, clamps, or whatever. And actually, these generative models can also be used to boost or to detect anomalies or discovery potential. And this is not an example in astronomy, but it's an example on medicine. And basically, what you can do is you can use the generative models, and we'll talk about this later on. You can use the generative models to generate, for example, you take healthy data of images of people, and then you generate these generative models to create some healthy data, to generate fake data, but of healthy people. And then when this model is confronted to people with some kind of disease, then the model is able to identify that this was not the data it was trained with. So it's a way to identify anomalies, in that case diseases, but in our context would be objects that are not in our expected universe. Again, generative models can be used to deal with the convolution, and this is something, a complex problem also that requires dedicated software, so deconvolving or removing the PSF effects. And basically, you can train a network to, from a degraded image, try to recover or deconvolve the data. Okay. So just to put some formalism on this, and I will stop again with the equations, but basically just to introduce some terms that I will be using during the lecture. So basically, again, so supervised learning, the way it works is that we have a data set with known labels, which we call measurements, and that we use to predict from these measurements on an unlabeled data set. So basically what we call X are the measurements, the vector X, which could include all typical measurements we use in astronomy, color, fluxes, spectral indices, blah, blah. And we have a label that we want to predict, which could be morphology or a transit or an object type, and we want to learn a mapping between these two. Basically, what we want to learn is this function that f that maps between the two. So that when you go with an unlabeled data set, you are able to predict the classes or the parameters, the labels for this particular unseen data set. Okay, so the general goal then is to find a nonlinear function that outputs the correct class or the measurement for a given input objects. This function is, takes as input the measurements, and what you have is a function, which is a general function, which is parameterized by some weights, as we heard this morning, and this is the number of weights that you can minimize can be quite large. So you want to find the W such as the prediction error is minimal over all the unseen vectors. And this is the basic of all machine learning algorithms. And all the machine learning, there are a bunch of different algorithms as we see this. So you will learn about supervector machines probably by Michael. You will learn about random forest or decision trees. I will talk more about artificial neural networks and how they, because they are the seed for deep learning. But basically, the idea behind all these algorithms is always the same. You are trying to learn a function that maps the measurements into an objective, a label. And the differences between all these algorithms basically in the function you use to map this. Okay? So neural networks use a specific function that I will emphasize now, and these random forests or supervector machines, or the perceptron, as we saw this morning, use a function over here. But basically, the problem is always the same. And you always need two key elements for every machine learning algorithm. One is a loss function, so which is what is the one you want to optimize, basically what is how do you measure your error, and a way of finding the best way. So an optimization or minimization algorithm. Then in machine learning, we call optimization algorithm. But basically, you have a function that depends on some parameters, and you have an error, and then you want to find the parameters that get the minimum error. And this is common to all machine learning algorithms, I guess. So basically, what you do is you have a loss, what we call a loss function, and basically is given the measurements and the label, you want to find what is the error that you do when you apply your function to the measurements for a training set for which you know the labels. So for example, a typical error that you can use is that the quadratic difference that you use for chi-square fitting, for example. And basically what you do is you apply your function to the measurements, and you measure for this. So this gives you a label that you compare to the label that you know is true for the training set. And this is your metric, basically. And once you have your metric, you try to minimize and to find the weights. Remember, what you're trying to find is W, because this is what parameterizes your function, that makes this loss minimal. So this is very typical, and this is what you do, for example, for chi-square fitting. The only difference here is that you don't know what this function is, or at least you put a general function. It's not a function that is a model that is specific to your data. You put a general function that depends on some weights. But basically, what you're trying to do is just minimizing. So an important thing is that we are minimizing the empirical risk. What does that mean? This doesn't work anymore. Yes. What does that mean? Since I guess this is supervised learning. So again, you are based on a training set, and the training set is just made of a finite number of observed examples. So basically, what you are assuming, so you are finding the weights that minimize the loss for a given number of objects that is part of your training set. And this is important because, in fact, you are assuming that your observed data set or your training set is representative of all reality. Let's say you are going to train on this particular data set, and then you are going to apply it to a blind data set. And you need to have always this in mind, because this is a very important bias of machine learning. So for example, if you have an observed data set, and you will then use in this observed data set to generalize to all the observed universe. And we know that astronomy is particularly sensitive to biases and selection biases. And you need to be very careful about this when you apply machine learning. Let's, for example, put a stupid example. But if you want to do galaxy morphology, and you take a data set of, you go and you point Virgo. And in Virgo, you observe that 95% of the galaxies are elliptical. Okay? And you use this as a training set to separate between elliptical galaxies and spiral galaxies. So what your machine learning algorithm will do, okay, this is easy. If I say that all galaxies in the universe are elliptical, I'm 95% right all the time. So I'm done, okay? And you have a machine that is completely dummy and is saying that all galaxies are elliptical. So you need to and so this is because you are minimizing the empirical risk. And you are making a strong assumption into saying that your observed data set is your total data set. So you need to be very aware of biases when you train your algorithms. So in practice, the way we overcome this, and I think is, we'll hear about this a lot, but basically you always use what we call a training set to optimize. Sometimes a validation data set that we use in neural networks, but I will show you this later. But basically, you train your algorithm, you find your weights on a training set, and you will test your algorithm in another data set, which has never been seen by the network, which is the typical problem of training and testing. Again, if your biases are in both, then I mean, this doesn't help, but at least it's a first test to see how well your network or your algorithm is able to generalize. So you will never use the same, the algorithm, the data set you use for training, you will never use it for testing your algorithms. So please, no cheating. This is very important. So, and then again, I'm saying this because I've seen papers accepted in astronomy in which people are using training and validation in the same, so the same data set to train and validate, and this is completely wrong, okay? So please, no cheating. You use always a different data set to train and validate. Now, the algorithm, so this is the part of, you find you have a loss that you want to minimize, and then the second ingredient is optimization or the minimization. For us in astronomers, minimization is the term that we know more. But basically, then what you need an algorithm to find the weights, to minimize the minimum weights or to minimize the loss. And the algorithms that you will use depend, again, on the machine learning algorithm and what is the function we're trying to minimize. So neural networks, as we will see later on, use a very simple way of minimizing, which is the gradient descent. And basically what you're trying to find, so again, you're trying to find the weights. And what you will do is basically follow the slope of largest gradient. So you have a function that depends on the W. You compute the gradient, and basically you follow you look for the minimum by following the gradient. So this is the simplest algorithm that you can imagine to minimize. Again, I will give you some vocabulary, but I will go back to this. So you have what we call the learning rate is the rate at which you update your gradient over here. And basically, what you call, this is the weights that we learn, and the T here is the epoch, because you will iterate at several times. I will go back to this. It's just to so that you have in mind that there are two main ingredients, a loss, and then you minimize this loss with an optimization. So again, you have a bunch, so to go back to this, you have a bunch of different algorithms. And I think the question was asked already at some point, how do I choose my favorite algorithm? So all algorithms can do similar things, but work differently. So how do I do as a practical, from a practical point of view to select the best algorithm for my problem? I think from my point of view, but maybe my colleagues disagree, that there's no rule of thumb to see what is the best algorithm. It really depends on the application that you want to use, for what do you want to use them. I put here some advantages and disadvantages of some of them. For example, random forest, as we see, clearly the advantage is that very easy to interpret, so you can understand very quickly or very easily what the algorithm is doing and what are the best parameters so inside the algorithm. But it can be you can clearly go to over complex trees depending on and it can be somehow unstable and depend on the training set. On the other side, you have neural networks, which are the seed of deep learning, and this is what I want to focus on. These are very efficient with large amount of data, as I will see, and to find correlations in the data, but however are very, very difficult to interpret. So it's, especially if you go to deep learning, it becomes sort of black box, although I will try to put it a bit whitish, but it's very difficult to interpret. So again, it depends on what you want to use. All of these, as we will see, are easy to use in Python, and I put here some of the. Again, you can choose your algorithm depending on your main interest. Again, for example, you can put here in the y-axis interpretability. So how easy are, so I really want to understand what the algorithm is doing. So basically, you will go through decision trees, for example. And you see that deep learning is far here. So if you really want to understand what your algorithm is doing, because it's very important for your science, you want to classify objects in different classes, but you really want to know if the mass, the stellar mass is important. So this is something that you won't be able to answer with neural networks, because neural networks will probably achieve a very high accuracy, but you don't know exactly what are the parameters they are using. However, decision trees are very efficient for this, so because you will quickly see that the stellar mass is very important in determining your property, for example. And again, it's also influenced by mainstream trends. And for example, this is a function of the year, how the popularity of the different algorithms changes. And you see that neural networks, the perceptron was here. As we see, neural networks gained some popularity, but at some point, we decided that they were not useful because we got stuck and there were no much progress on neural networks, so popularity decreased. And you see that in the early 2000s, SVM were very important. And now you see this is deep learning, okay? Because so deep learning is this, neural networks are the seed of deep learning, so it makes these tremendous jumps in terms of popularity. Okay, so I will continue with the part 2, which is on neural networks. So again, my lectures are intended to introduce deep learning, and neural networks are the seed of deep learning. So I will go a little bit on detail on how these algorithms work. Any question? Okay, so I will first go quickly because we already had some nice introduction by Michael. But basically, neural networks are somehow inspired by neuroscience, although the comparison doesn't stand very long. But basically, the idea is that you have an element, which we call the neuron, and that have several inputs and one output, essentially. And the output will depend on a kind of weighted sum of the inputs. This is how an artificial neuron looks like, and it's the same idea, and you have several inputs. The inputs will correspond, again, if you look at the X here, with the measurements, and you will multiply this measurement by some weights, and then you apply here an activation function, which is nonlinear, and that introduces some nonlinearity to the process, which is completely linear. So I go into details into this. So I will skip this, but I also intended to start with the first neural network, which is this hardware perceptron. But we heard already a lot of this, so I will skip it. So what is today artificial neural network? So let's introduce some terms here. So basically, the idea is the same. Again, so to go back to what I said at the beginning, you have a set of measurements, which could be for a given object. You have colors, you have sizes of objects, for example, if you want to do morphology, or Sersic indices, or whatever measurement, or spectral indices, whatever measurement you have on your data. And then what will happen here is that basically you input this into a neuron over here, and the neuron simply multiplies every measurement here by some weights, W. So remember, this is your network function, and the weights is what you're trying to minimize, W. You can add some bias, some additive term, but this is not important. And once you have, so basically you take your measurement, you multiply by some weights, you add the bias, and then you add a nonlinear term, which is called the activation function. I will go back to this. And this is basically your network function, okay? Remember, so we talked about network function. This is a general function that depends on some weights. It's nonlinear because of this term over here. And basically, you're only taking the measurements and getting some function that depends on the parameters. This is what an artificial neuron does. Of course, you can put several neurons together. And in fact, unless of having W, which is a vector, it becomes a matrix, because you have all measurements that every measurement is multiplied by a series of weights, which every weight is dependent on a neuron. Okay, so you can stack neurons together. But again, it's the same idea. So W, this pointer doesn't work very well. This is W here, which becomes a matrix, but at the end is the same thing. So every measurement here is multiplied by a series of weights, and then, again, bias and the activation function over here, and you have a series of outputs here of every neuron over here. And then, so you can stack them like this, and you can also add some complexity by putting one set of neurons after the other. Then, for example, here, so you have your input over here. You multiply by the weights. You have the output of the first set, which is, again, Wx plus the bias, and you have the output over here. And then once you have the output of your first layer of networks, you use this as an input as another set of neural networks or neurons, which is another layer of neurons together over here, which will take the first input over here and do exactly the same operation. So from the first set of the first result over here, you do exactly the same operation over here, and you can go so on and so forth until you get to an output layer. So basically, you are nesting one after the other. So you can, so you have, yes?
Is it still useful if you're using the same activation functions?
Yes, so the same activation function, but you're using different. So basically, what you are increasing here is the number of parameters of your function. So you have a function that depends on some parameters, W, and by adding, stacking, putting hidden layers, you are increasing the number of parameters, and you are increasing the nonlinearity, because at every step, you are passing through the activation function. So you're nesting and doing more complex functions, essentially. But the idea is essentially the same. So to go back to this picture here, this is in neural networks, this function over here, okay, that depends on some weights, is basically this nested function in which you take the measurement, you multiply by some weights, you apply the activation function, then you multiply the output of the first layer by some weights, you apply the activation function of the second layer, you multiply by weights, you apply the activation function, and so on. So at the end, you get a nested. So this is your network function in which you have lots of parameters here, the weights, and the nonlinearity which is introduced here. And this is my network function. Why you want to introduce some hidden? Yes?
Does the number of hidden layers,
yes.
if you increase it, does it necessarily make it better?
This is what excellent question, but this is what I'm trying to answer here. And this is the, so again, why you need hidden layers? And so the question was, if I increase the number of hidden layers, does the result, is the result better? And the answer is no. But why you want to do hidden layers? Again, so hidden layers makes your network function much complex, more complex. Again, you're introducing more parameters and more nonlinearity, which means that you can create more complex functions. So you can solve more complex problems. For example, in this classification problem in which you're trying to split the red points from the green points, depending on the number of hidden neurons that you use, you will be able to create some complex boundaries, okay? Now, if I ask you to separate the green and the red, it doesn't mean that this solution is better than this one, right? Why? Overfitting, right? Because this solution, so in the training set, it's perfect, okay? It's able to, basically, you are putting all the red points in one class and all the green points in one class, right? But when you will apply this to a blind data set, so basically, if the data point falls over here, so if the test data set doesn't follow exactly the same pattern, which will be the case, you will commit a lot of errors, so your error will increase. So what happens here is that the function is too much adapted to the problem, to the training set, okay? And this is what we call overfitting, as we'll see. So basically, it doesn't mean that it's better using hidden layers, but you increase the complexity and you can create more complex problems. So now you need to find a balance. And this is part of what we're trying to learn here. So again, this is what I was trying to go. So if we can do more complex, go deeper and deeper. But again, so if you go deeper and deeper, it's not so trivial. So it's not a matter of, deep learning is not a matter of adding layers, because if you add layers, deepens more weights. It's also more difficult to optimize, remember, so you are trying to find the minimum of a complex function. If you start adding weights one after the other, you have a very complex network function that you need to minimize. It's not trivial. And again, you have the risk of overfitting. Yes?
Do you know when the
The number of layers? Well, again, the question is, how do you know the number of layers that you need to use or number of neurons? There's no there's no simple answer to this, but it depends on what you're going to achieve. And the way to do it again is by using a training and a test, and you check, for example, for overfitting. So overfitting is very easy to identify in the sense that you have your training set. It might work perfectly on your training set, but then you go to the test set and you realize that the performance is very poor, because for the test set it's something that you still know the answer, you can try it, and then this is something that you can use, for example. But again, it's very hard to know when you use neural networks to make sure that you are using the optimal architecture. And so these are techniques to find the hyperparameters, the best combination. But there's no, so I will talk about this last day, but it's not trivial to find what is the best architecture for a given problem. So, yeah.
But in general, like, is there a rule of thumb for, I guess, the number of hidden layers and number of hidden neurons being limited by the dimensionality of the data?
So this is a good question again. So the question is there a rule to decide what is the number of neurons depending on the data? I think, again, so what the techniques I use are mostly empirical. So basically empirical. So I don't know a way, so of course, if you have, if you have a data set which is 3 dimensions or 3 parameters, you are not going to use, yeah, exactly. So this is something that you need to look, it's common sense at some point. Now, I don't think there's an easy way to say for this particular problem I will use a 3-layer, or for this particular problem I will use 5 layers. It again depends on the complexity of the problem. If it's linearly separable, for example, then it's probably with 1 layer it's enough. So it depends a lot on the data you have. Again, the way you do it is more empirical, so you go to the training set and you try on the test set, and you try to play with the hyperparameters, so you can change the hyperparameters and see how the performance changes. But it's not, at least to me, from my experience, there's no easy way to find the best architecture for this.
An increasingly complex network would probably require more data for training.
Exactly. So this is, then you hit overfitting, right? So if you increase the number of layers, if you stay with the same amount of data, then you have the problems overfitting. It's like when you are trying to fit a polynomial of order n into n points. So basically, it will go through all the points, but it's not a good approximation or a good modeling of your data. Yeah. Yes, so so the way to quantify overfitting is empirically is by using the test data set. Because overfitting is one of the things that are easy to find. It's not the most complicated things to find when you train a neural network. Because if you have your training set and you have your test set, you can very easily measure the difference between both. And it's very easy to find, because you see that when the overfit, you can have subtle overfittings in which the difference is not so high, but when you have a dramatic overfitting, you clearly see it in the test data set. Questions? Yes. Okay. Yes.
When you're deciding the weighting of the parameters.
Sorry?
When you're deciding the weighting of the parameters, the inputs, to what extent do you choose the weighting and what extent is it physically motivated?
Okay, so the question is, how do you choose the weightings of the parameters, and if the weights are physically motivated? And I think the answer is no. So this is the problem of neural networks, or one of the, so the weights are not translated into a physical meaning. And if you go to deep learning, it's even worse, okay? So it's, the weight, and there's lots of work which is called network introspection or network interrogation techniques, in which you try to understand why the network is doing some decisions, as I will try to show you later on, but it's not a one-to-one problem. It's not that you say that this particular weight is measuring, it's sensitive to the size of the ears of the cat, for example. It's not something that you can translate into a physical meaning. And this is important for astrophysical applications, for example. That's why I was saying at the beginning, if you want to have something that is very easily interpretable, so that you can understand what the algorithm is doing, probably neural networks is not the way to go, okay? Although it's getting better. Okay, so before we go deep, let's try to examine more how simple shallow networks work. And I have some 5 minutes, so I think I won't have time to this. Just I want to go again. So a neural network or a neuron has two basic steps. One is linear, very simple. I take the feature space over here, the measurements. I multiply by the weights. I add a bias, and then I apply a nonlinearity over here, an activation function. So what is a typical activation function that people use? These functions are nonlinear, and they are close to a sine function, as we've seen already. And you have different terms, kinds of activation function, but they are basically pretty simple. And essentially, these are close to step functions or sine functions, in which the response, if you are below a threshold, is very low, close to 0. And if you go above this threshold, then the response, the output, is larger. This is basically how all the functions work. So these are the sigmoid function that you probably will hear if you work with neural networks. This is the ReLU function, which is basically 0 below 0, and then it's just linear over here. And this is very used in deep learning, as I will show you later, because it's more stable. So this is only for your records. All these are the typical activation functions that you can use. So again, this is what the nonlinearity that you put after the neuron. So these are the definitions. So it's for your records, so you can go back here, because when you tune your neural network in Python, for example, you will have to choose between different activation functions. And these are some impact. We'll try to show you this a bit later, but this is the meaning of this. But essentially, all have a very similar behavior, and others. So what is the meaning of this activation function? Again, I will try to explain this with hands, let's say, but is basically, if you think about this trying to create complex functions, because basically you have a set of measurements, and the mapping between the measurements and your label might be complex, nonlinear. So you want to have a function f which is general enough that is able to map this complexity of your data. And it basically, if you think about it, so any complex function can be very easily approximated by a combination of ReLU functions. I remember, so ReLU functions are the ones which are 0 and then linear, scaled differently. So for example, if you want to imagine you want to use a neural network to approximate this function over here, but basically it's very easily done with combination of different ReLUs over here that you scale you scale differently and you translate. So basically, by introducing this nonlinearity, you are able to reproduce complex functions. So it's very easy with hands. I'm not entering into details again. I just want you to have the meaning, more or less, of this idea over here. Yes?
The more input you get, or the more information you provide to the system, the better, and the less levels, the better, or not. Let's suppose you work with the dogs and cats, that there should be a certain category. I don't know.
I'm not sure I understand your question. I think what you're asking, so you said the more data I have, or the better, or you mean you're talking about the measurements here, the X?
Yeah. Let's suppose we are classifying cats and dogs, and you the image, but you can include also the weight you want.
So again, so the question is, this is will part of the next lectures, but basically you are touching a very important point, which is how good need to be this feature space over here, so that you get so this is not magic. Okay, so basically, if you are trying to solve a problem over here, a labeling, and the features over here are not the optimal ones, okay, let's say for this won't do magic, it won't solve the problem, okay? And this is, for example, so again, if you are trying to distinguish cats and dogs, and basically you are using, for example, the size of the ears, of the eyes or something, but you are missing something very important, then it's probably, for example, if you have a cat with the eyes closed, and then you are using the size of or the color of the eye, this won't work, essentially. So basically, you need to find the optimal features over here. And this is a very important problem. And this is where deep learning is important. So I haven't had the time today to enter into this. But basically, what deep learning is doing is finding the optimal features by itself. So it's not, you that you are measuring these features is the network that is finding it for you. But this is for tomorrow, okay? I should stop here? Okay, so I'll stop here, and then I'll take some more questions if you have, and continue tomorrow with CNNs, and thank you. Yes.
So in this example, where in the definition of the ReLU activation function is the translation encapsulated? Because so it seems like when you translate each version of the ReLU, you have to do that specifically, right? You have to choose some number of translations that you want to use, and then each one of those is like an independent basis function, right?
Yes, so this is just an illustration of how it more or less with hands, it's not what the network is doing by itself inside. It's just to let you, so to illustrate that basically what you are encoding with this nonlinearity is that you are able to reproduce. So if you include only the weights and the linear multiplication of the data, you cannot reproduce nonlinear functions. That's why you want to include this nonlinearity in the process, basically. Now, how is the translation, if your question is how is the translation invariance taken into account, so translation invariance is not something that you have in neural networks by default, but for example, CNNs are. So, and this is convolutional neural networks are by definition translation invariant, and this is one of the reasons why they are so successful in classifying objects. And I will explain this in the next lecture. Yes?
So the perceptron is like a single layer.
Right, exactly. Well, not a single, yes, it's just one element of a layer, right? So the so you have two things. So you have a vertical stacking. So this is, a perceptron will be, so again, I repeat the question. So she's asking, what is the perceptron? So the perceptron that we heard this morning is just one element over here, basically, okay? So then you stack perceptrons vertically, and then you put them in different layers. This is a neural network. Is that the question?
Yeah, you answered.
Okay.
I think we should stop there, so thanks very much again.
Thank you.